We're going to pause and do a little mathematical interlude. I might do this from time to time throughout the series. Quantum field theory is notoriously a very difficult subject to learn, maybe one of the hardest in all of science, for a lot of reasons. I'm trying to show you that it's really inherently not that difficult, especially if you're already able to understand quantum mechanics. One of the difficulties, though, is also there's a lot of math that comes into play. Sometimes it's new, a lot of different fields, and it's tricky. It's tempting to say we should, before you take quantum field theory, take a full course in complex analysis and things like that. But then realistically, it would just put off so many different people and make the learning curve so steep. So I'm going to try to do these mathematical interludes from time to time, just to kind of go over the relevant math in a more intuitive way. I'm not a mathematician, I'm not even a physicist, but just in the way that I kind of understand things. And I think these are important. Instead of throwing it all at once in the beginning, where it's also intimidating and you never get to the exciting stuff that you came to learn about nature, it's sometimes good to intersperse it a little bit. So I broke this lecture up into just this mathematical interlude part, so it'd be a little bit easier to follow it on the playlist. So this mathematical interlude we're going to talk about, I just mentioned at the end of the previous lecture that when you get to the continuum modification, you have to switch the Kronecker delta to the Dirac delta. And I'll try to explain a little bit why that is. People may be familiar with this already from quantum mechanics, but it's still worth seeing some of the things. And again, talk a little bit about our conventions for the Fourier transform. I won't get into full detail with it. Hopefully at this point you've seen some of that before, but I want to go over some important things. So why, at the end of the previous lecture, do we say that when we go from discrete representation of things to a continuous representation of things, for example, for voxels being discrete to voxels being infinitesimally small, why do we switch from the Kronecker delta to the Dirac delta over here? And this is the symbol for the Kronecker delta, where we have a delta, and then just the way I write it underneath, I have one argument, comma, another argument, versus the Dirac delta, I have this, and then one minus the other. Sometimes you'll just see this, implying that this one is zero, and similarly here too. But that's just the way I define it. Suppose we break space up into a bunch of voxels, like we've been doing all along. For example, for a moment, just don't think quantum field theory. Let f of x be a real valued function defined on all voxels, meaning you give me a voxel, I'll give you a real number. One important example of such a function is this, the Kronecker delta function, delta x comma y. Let that be a function over all voxels that is equal to 1 on voxel y, but 0 on every other voxel. So that's the way we write it. It's a function of all voxels x, and then x, and I usually put a comma sign here, which I apologize I don't have. Just throw that in right now. X, if it happens to be equal to y, it's 1. If you're talking about any other voxel other than y, then it's equal to 0. And that's how we write that over here. This you can call the Kronecker delta function, let's say, for a three-dimensional space. A lot of times we're going to have to sum over all voxels and add the value of a function at each voxel. So when we do that, if we just had this thing over here, if we add over all voxels, this voxel, this voxel, this voxel, this voxel, this voxel, let's just say this is the voxel where y, let's just say where the function is equal to 1, then only in this voxel will we get the number 1. When we add all the other ones, we'll obviously get 0. 0 plus 0 plus 0 plus 0, plus 1 equals 1. And that's what we get here. Now, what's the equivalent of this when we have a continuum? What's the equivalent of the Kronecker delta when we have a continuum? Well, if we change to a true continuum, in mathematical physics, we still do a sum, but the sum changes really to an integral, which is symbolized like this, basically implying that we're summing over an infinite number of terms, each of which are quote unquote infinitesimally small, or they represent an infinitesimally small part of the function rather than the sigma term. But really what happens here, which is very important, is whenever you switch to in physics, whenever you switch to the integral, you don't just switch to an integral sum, you always add this term dx. That's just the nature of way all mathematics is set up. You have this integral times integral over dx, which means you're not really just doing a sum. It's not just a sum. It forces us to multiply each term in the sum, when we do this big integral, by an infinitesimally small constant number dx. So you're adding to you're not just summing every term, but within every term you're multiplying it by dx each time, and then you're adding the results. If we want a continuum analog of this, we need to offset this tiny dx by multiplying the non-zero term, the x equals y term, by 1 over dx, which is infinitely large as dx equals 0. And I'll show you what that means in the next slide. But basically, if we're going to add up everything and we're multiplying everything by the tiny term dx, including the term where actually, the value of the function or this Dirac thing is 1, if you take 1 times dx, that'll just get infinitely small, and that'll add 0 to the sum. So you have to offset that by making the Dirac function here not just equal to 1, but 1 times 1 over dx. As dx gets infinitesimally small, that's essentially going to infinity. Show you what that means here. So instead of the Kronecker delta, we therefore define this function called the Dirac delta, where if you take the Dirac delta of x minus y, that's equal to 0 if x is not equal to y. So same as what we were talking about before. If you look at every other voxel where other than y, this is equal to 0. But if x equals y, then this thing is equal to not 1, like we did for the Kronecker delta, but 1 over dx to the third. This is the 3D version of it. This number is essentially infinite if dx gets infinitely small, so you'll often see this written as just infinity. But probably a better way is to write it like this, 1 over dx to the third. Now what happens? If you do the integral of that, integral over all space of d third x, this is just a 3D version of what I was talking about before, where you're now multiplying each sum in the term by this, you will get 1. Why? Well, here it is. If you do the integral of d third x of the Dirac delta x minus y, you get 0 times dx to the third. This, for example, can be an area where x is not equal to y, 0, where another area where you're not talking about y, and then plus, plus, plus a bunch of 0 terms. And then when you get to the term where your x equals y, the thing is not 0. This function is now equal to not 1, but 1 over d third x. And then when you multiply that by d third x, these two d thirds will cancel. And then what you're left with is what you desire, 1. So that if we desire something where we have this function over everywhere where it's only defined at one point in space, and we want the integral of the whole thing to equal 1, you have to change the Kronecker delta to this Dirac delta, and this shows you exactly why. Of course, if you did that with the regular Kronecker delta, if you just expand this sum, you'll just get d third x. There would no be 1 over d third x, so these wouldn't cancel. So you have 1 times d third x, and the rest of them are 0, and d third x would really approach 0 rather than what you desired as 1. So this is why you have to switch from the Kronecker delta to the Dirac delta. Similarly, this formula comes into play all day long in quantum mechanics and in quantum field theory. If you take this integral of d third x of this same term here of the Dirac delta, but within it you multiply it by f of x, what ends up happening is that this just samples the number at the point f of y. So this whole thing equals f of y. And this is the argument y. It's the same exact thing. Instead of just this being 1 everywhere, now it's this part here is 0, 0, 0, 0, 0 everywhere. But when you actually get to the point where x equals y, this thing ends up being 1 over d third to the x times d third dx. These will cancel, and you just get f of y. So this thing is kind of like a sampling function, and this comes up all day long in quantum field theory, where you just get this thing ends up sampling this function and just giving you the value f of y. Fourier transform, again, not going to get a lot into this, but I'm just going to go over the intuitive important parts. Recall that if we have a periodic function of period t, we can express it as this. I've kind of changed this a little bit, but roughly speaking, remember, if we have a periodic function of a finite period of t, we can say f of x is equal to this kind of sum over p of e to the I px's, and these p's can run from positive to negative. You can have complex conjugates and other restrictions on AP, but roughly this is how we can define things, and we put some restrictions on p related to this period. If we have a non-periodic function, which if you think about it really means that if you go to infinity, the function could be periodic over infinity, but that's what a non-periodic function is. We can still express it in similar form, but instead we use the Fourier transform. It's kind of like the difference between discrete and continuous that we were talking about before. In a similar way, you can still express f of x as a sum of exponential functions, e to the I px, but now that sum becomes an integral. So f of x can be expressed as this integral over here. where instead of summing over all the various e to the IPX's, you have a continuous sum, d third p, where you can vary this continuously. There's no restrictions on p. They don't jump in discrete amounts. And then you have some coefficient, which you call the Fourier transform. These are just the coefficients of this expansion. Now, when you do Fourier transforms, this part causes a lot of confusion. Different books use different things, and it sometimes can cause a headache in the calculations. When I do the continuous analog, I really like David Tong's notes a lot. So I want you to be able to also look at those and relate to other books that are out there in quantum field theory. So I'm going to use his convention where he always puts a 1 over 2 pi to the third every time he puts a d third p. So just every time you see d third p, you'll see 2 pi to the third. Later on, you'll see d fourth p, you'll see 2 pi to the fourth. That just is the way he has the convention. There's 2 pi factor actually has to go somewhere. More can be said. What exactly are these coefficients? Well, according to the theory of Fourier transforms, the Fourier transform f of p satisfies this, that you can find f of p by integrating the original function over all of space multiplied by e to the minus ipx. And if you step back and look at this, one way to look at this is that the way you get this coefficient is exactly plug it into this formula, which is well defined because f of x is already well defined. The other way of looking at this is this f of p could be thought of as another function, which can also be expanded because it's just another function by coefficients f of x. So these are the coefficients of the exponential function. These conventions are important. That this is positive IPX here, and this is minus IPX here, and there's no 2 pi to the third by convention that David Tong uses in his notes. Klauber uses mostly discrete forms, but the analog, and sometimes that he puts explicitly, is a d third p over the square root of 2 pi to the third. So you have the square root of 2 pi to the third becomes the same on both sides. I won't really be using that part, although I'll use Klauber in other ways, which I'll show you. I think we've shown already. If we apply this to the Dirac delta function, we get some important result here. That remember the Dirac delta function now, like I defined it as this. Here I just got rid of the x minus y. You can think of it as y equals 0, but the Dirac delta function of x is equal to 0 if x is not equal to 0, and 1 over d third x if x equals 0, which this is just, you could basically think of it as infinity as d third x gets infinitely small. But infinity is a little bit of a vague definition. This is a little bit more clear. If we just follow through our logic, by the definition of the Fourier transform, the Fourier transform is equal to, just from the previous slide, of this is equal to integral of d third x of this times e to the minus IPX. That's the definition. These are if you expand this out exponentially and you look for coefficients, you get these coefficients, and this is how you get it. And if you just follow through the math here, this Dirac delta function is 0 everywhere except at x equals 0. It's a sampling function in this case for this function at x equals 0, so you get 0 everywhere except at x equals 0. This is 1 over d third x times here, because we're doing integral, we also have this d third x factor. These guys will cancel, and then you're left with this, which is the value of this function at x equals 0, which is e to the minus ip0, and that e to the ip0 is e to the 0, which is 1. So the Fourier transform of the Dirac delta function is equal to 1, symbolized here. Now, if you go back again and just say, okay, now I know the Fourier transform, I can re-express this function as an exponential sum with these coefficients, just using the formula from the previous slide. The Dirac delta function is equal to this, integral over d third p over 2 pi to the third. These are the conventions we're using according to David Tong, times the coefficients, which is the Fourier transform, delta p, e to the IPX. But we just proved that this thing here is equal to 1, so that factors out. And this is an important formula that we get, that the Dirac delta function can be re-expressed in this form as the integral d third p over 2 pi to the third of e to the IPX. There's a discrete form of this, which becomes important as well. Let's look at this integral. Integral over all of our volume, where let's say over our experimental box of d third x e to the minus ip dot x. Let's try to figure out this integral. Let's just think of two cases. Suppose p here is equal to 0. Well, then this whole term equals 0. this whole term, this whole exponent equals 0. So e to the 0 power is just 1. So you have the integral over all of volume of the number 1, which just gives you the total volume of our experimental box. And this volume is the experimental box. We keep the restrictions on p here, let's just say, to those values which make e to the minus ipx complete an entire cycle over a given side of the volume box, as we talked about before. Let's say case 2 for this integral, that p is not equal to 0. Well, then the integral is equal to essentially, quote unquote, the area under the curve. I won't get into this in 3 dimensions, but it's a natural extrapolation, I think. In 1 dimension, if we're restricting p to those p values that cause e to the ipx to complete an entire cycle over a given volume of the box, as we talked about in the previous lecture, we may have, if we just look at, for example, the cosine or individual sine components of e to the ipx. I'm just going to pick one of them. Let's just say this happens to be the, depending where we started, this happens to be the sine component of it. If it completes an integral number of cycles and we take the integral of this whole thing, remember the integral is just the area under the curve, all the times when it's positive are offset by exactly by the amounts that it's negative, and same here and same here. So this whole integral will end up equaling 0. Same thing in 3 dimensions. So when p is not equal to 0, this thing is equal to 0. This gives us our very important result, which we will use again in the next upcoming lecture, that the integral of d third x of e to the minus ipx is equal to this, v times the Kronecker delta, meaning that if p is equal to 0, these two terms latch, this thing gives you 1, and this whole expression is equal to v, which is this right here. But if p is not equal to 0, then you take the integral d third x of this, and then you end up getting 0. So if p is not equal to 0, this thing equals 0, and 0 times v is 0. So this is the important expression that we get from that. You can naturally extend this to if you had things like e to the minus I, not p, but p minus p prime, two different values of p. This you could just think of p prime as 0 over here. And very similarly, you would get this kind of relationship over here. That's equal to v of the Kronecker delta of not p with 0, but p with p prime. This is Kronecker delta times v. And same thing, if you do p plus p prime, you'll get a similar thing, except you get a Kronecker delta of p comma negative p prime. And once you understand this, not too hard, take a moment and just make sure you understand this. Take a minute to kind of recreate the argument if you like. And you could do the same type of thing as if this minus sign was positive, and same thing with these. So we have all these equations here. These equations will be very helpful in the next upcoming lecture. Another needed result, which we'll need on the very next lecture, remember this is a mathematical interlude about the QFT. We were getting into the QFT energy eigenstates, and that's our next lecture. But I took this little break to go over these important things about infinities, Fourier transforms, Kronecker deltas, Dirac deltas, and different expressions. Another needed result, in the way at least that I'm formulating things, is this over here, that if you take the sum of e to the ipx, not the integral sum, but just let's say the finite sum, but you restrict p as before only to things that complete an integral number of cycles, positive and negative, you get this. This is what I'm going to somewhat assume or just tell you, and I'll tell you why, but it makes one assumption. You get v times Kronecker delta of x and 0. Why? Well, let's look at this sum. If x is not equal to 0, then you're taking a sum of a bunch of exponential functions. But I'm not going to get into all of it because I don't want to detangle too much over here. But once you take the sum of a bunch of exponential functions with these p restrictions, and p could be negative or positive, these integral restrictions over the experimental box, all of those oscillations will perfectly balance out. And you can argue that. I'm going to show that here, but you can argue it. And you get the number 0. So when x is not equal to 0, and you try to do this sum, you will get 0, which explains this part over here. When x is not equal to 0, this is 0, and the whole term goes to 0, because all these exponentials vary in different ways that perfectly balance each other out and give you 0. What about the case when x is equal to 0? Well, when x itself is equal to 0, this is 0, and then this whole exponential is 0, and then you just have e to the 0, which is 1. So then you just basically have this sum, a sum of you just keep adding 1 to itself. How many times? well, all the possible allowed values of p. This is where things get a little bit tricky and a little bit different, maybe between the different books, including mine. It actually differs a little bit from Klauber and Tang. Um, what is this sum over here? Well, if we let p be unbounded, even though if it still follows these restrictions, but there's no final positive or negative limit to it, which is what I mean by bounded. If it's not bound, if it's unbounded from above and below, this thing should equal infinity. 1 plus 1 an infinite number of times should give us infinity. However, I think you can argue that to be quote unquote symmetric with our prior result for a bounded volume, which we just showed on the previous slide, where we have this formula, the integral of d third x of e to the minus ipx is equal to v times the Kronecker delta of p and 0. Remember when we did this formula, if p is equal to 0, this whole thing was not infinity. We were adding 1 to itself, but how many numbers of times? Not an infinite number of times. Why? Because we were doing 1 d third x times. So that we have to count the number of voxels, and that's how many times we add 1 to itself, the number of voxels. If we assume we're dealing with a finite box and not infinitesimally small things, the number of voxels, which is this over here, is not infinity. It's a huge number, but it's not infinity. It's equal to the volume of the box, V. I think really to be symmetric, this expression over here should end up matching this expression over here. And in other words, that will happen if we assume that our quote unquote momentum space volume equals our physical space volume. What does that mean? Well, if we cut off p above and below, we still want it to follow this restriction, but it's not going to go to infinitely large numbers and infinitely small. There's going to be a cutoff right above and below, so that the total number of p-values, if you count how many different possible p-values are allowed, is equal to the total number of voxels in our box. They're identical. So we are going to assume, for some arguments here, when we use the discrete form, that the total number of p's equals the total number of voxels. This might sound kind of wild, and I don't think this is explained or even assumed. Maybe I'm even wrong with it in a lot of quantum field theory books, but I think it's for what I want to do, it makes a lot of sense. If for those of you that have studied condensed matter physics, is a perfect analogy for this as well. When you look at the Brillouin zone, you don't have to go past the other Brillouin zones, and if you look at the allowed values of the momentum in condensed matter physics, for those who understand the lingo, it equals the total number of lattice points. So there's a perfect analogy and a very simple and beautiful proof that those two numbers are exactly the same. Quantum field theory, if you really want to kind of open your mind, if you start reading some solid state physics and quantum and condensed matter physics, has some wonderful analogies to that. In fact, I think that's one of the hot areas in quantum field theory is to apply it to condensed matter physics. And it gives you a lot of insight even to this. We're going to focus a lot more on the experimental particle physics side, just what makes up all of nature. I'm always interested in that question, but there's a lot you can learn there. And this analogy really is solid in condensed matter physics. That's kind of what I'll assume. It also helps get rid of some other problems of infinities too, I think, if you have a semi cutoff here. And that's at the end of this mathematical